I'm now going to continue my video series on Common Core Algebra 2 with this. Now, what is this? Well, it happens to be the vertex form of the quadratic function. Okay, this is a quadratic function here, and this happens to be in the vertex form. Now, they did not get this out of thin air. They didn't say one day, hey, I think this would look cool, and I'll just write it out like this. Now, if you were to go through Common Core, that's exactly what you would think. But we're not Common Core here. I tell you what they tell you in Common Core, but then I also tell you the rest of the story. Now, obviously, we know this is a function, not a relation. Now, I already told you the difference between a relation and a function. The thing is that this f of x, if you wanted to go a little bit further with this, you could actually write this out as y equals a times x minus h squared plus k. Now, why would we want to write it like this instead of like this? Well, I'm going to show you something. Something that you think, you're going to be sitting there going, this looks kind of familiar. And it should. Okay? Because what we've got, what I'm going to show you now, is called the standard form of a parabola equation. Watch this. I dug this one up myself. X minus h squared. Now that looks familiar, doesn't it? You betcha. Equals 4p y minus k. We said, man, that looks awful familiar to that. And it should. Because the 4p here functions in the same way as the a does. Okay? They're the same type of situation. They're the same type of term. Now, they're a little different. I'm not going to say that there's no difference between the a and the 4p. But their function is exactly the same. So basically, a is 4p. They're interchangeable. Okay. Now, I know if we wanted to get a little more technical, it wouldn't exactly be interchangeable, but we're not going to get that technical. On a basic level, a and 4p are exactly the same. Okay. Now, we'll get technical later, and I'll explain that later, but right now, on a basic level, a and 4p are exactly the same. And look, x minus h squared, x minus h squared. But why did I write this as y and k? Well, what if we were to subtract k from both sides? Well, here. Let's just write that. Y minus k. If we were to subtract k from both sides of this equation, now you have y minus k. What's this? This is y minus k. You see, it didn't just come out of thin air. It actually was derived from the parabola standard form of the equation. This was derived from that. Now, are these two exactly the same? No, they're not. But they're very similar, as you can plainly see. And that's why I showed you all this. So that you have an idea where they got all this from. Now you say, well, why is x minus h squared? Well, I'm looking into that right now, and as soon as I figure out exactly the exact reason why x minus h squared. Now, I know that x minus h squared is a perfect square trinomial. That much I do know. But where exactly they came up with it, I don't know. But I'm going to trace it down. When I do, I'll tell you why they have that x minus h squared. Okay? Obviously, using the a, or aka the 4p, you can then figure out what direction the parabola is going to go. Is it going to go up or is it going to go down? That's why I say they function the same way. Alright? So, you say, oh, so that's where they got all this from. Now, where did they get the h and the k? Well, the h and the k are the horizontal and the vertical coordinates of the vertex of the parabola. Now, the x and the y are two other points. They're the horizontal and vertical coordinates of another point. And I'll say this again. They are the horizontal and vertical coordinates of another point on the parabola. That's what they are. And what you're doing when you subtract h from x, you're saying that you're now going to establish the distance between point h and k and point x and y. I guess the best way to illustrate it is to show you is two different points. Here's h and k, and we're going to pretend that x and y is somewhere up here. Oops. I know my writing's a little sloppy, but there you go. Anyway, so if you want to know the distance between here and here, you would subtract h from x. And that's how you know the distance from here to here. And that's where you get that from. See what I mean? And that's why I showed you all this. So this equation didn't just come out of thin air. I'll show you another equation that looks very familiar to you. And you can say, well, this kind of looks similar to that too. Okay, so let's go ahead and erase this. Do you remember slope-intercept? I bet you do. y2 minus y1 equaling x2 minus x1. Remember that? Slope-intercept? Now, obviously, with a parabola, you don't have a single slope. Okay, you have an axis of symmetry in the whole 9 yards, and I'll get into that in a future video. But it works under the similar concept. Just like I was saying, the x minus h is x squared minus, well, it's not x squared, it's x2 minus x1. These are subscripts here, not superscripts. Okay, so under the same concept that this works, is the same way this works. And like I said, if this was turned into y and you subtracted k from both sides, we'll do it again. Y minus k equaling a times x minus h squared. Well, the y minus k is in similar terms to that. See what I mean? You're subtracting the y-coordinates of 2 points on your parabola, just like you're subtracting the x-coordinates from 2 points on your parabola. And that's where they get that from. So it's not like they just popped this out of thin air. That's ridiculous. So that's where they're getting all this stuff from. You see, if you dig hard enough, you find out this stuff. And that's what I'm doing now. And like I said, there's probably an explanation, a better explanation. That, well, they're saying, well, that's a perfect square trinomial. Of course it's a perfect square trinomial, but where did you get it from? And they haven't quite explained that one. And I will get to explain that as well. And when I do, I'll show you. Okay? But yes, this is a perfect square trinomial. It's just that it didn't come out of thin air. But now you have a better appreciation of this quadratic function because you know how this is supposed to operate. Okay, so it's not like they just wrote it down one day on a piece of chalk with a, they didn't just take a piece of chalk and write on a chalkboard, hey, this is what we think it's going to be. They didn't do that. It didn't come up from a puff of smoke. There were reasonings behind this equation, and I wanted to show you that. Go through that Common Core book, you'll never find the reasoning. Go through me and you will. So, there you go. Alright, that's all I've got to show you for tonight. The next topic I will cover, I want to tell you something. There is such a thing, and I'm going to go ahead and introduce this to you, and then I will go further in my next lesson. There is such a thing called the letter I in math. It's called the imaginary unit. And Descartes actually discussed this one. What is I? I is equal to the square root of -1. Why is I the square root of -1? Well, the main reason for this is that there is no answer to this problem. If you take the square root of negative 1, no number times no other number will create negative. You can't take a number times another number and create negative 1. It doesn't work that way. Okay? You say, well, what if you take negative 1 times 1? Wouldn't that negative 1? Well, technically, yes, but this is squared. You can't take negative 1 times negative 1 and get negative 1. See what I mean? No number times itself. I guess that's the better way to say it. No number times itself is going to produce that. So that's why they came up with the letter I. I is called an imaginary unit. And imaginary units can actually have coefficients. That's true. You could take 3 times I, or 5 times I, or 156 times I. You could even have x times I. You could do that. But even though there is such a thing called an imaginary unit, and Descartes actually discussed this in his book, and there have been other mathematicians actually establishing an imaginary unit. So that actually exists. Most mathematicians will tell you there is no such number set as an imaginary number set. Okay? There is no imaginary number set. I know that's a modern term, and they flip it around. They say, well, these are imaginary numbers. They are not imaginary numbers. They are imaginary. They're the imaginary unit multiplied by a coefficient. That's what they are. That is the proper terminology. And math scholars, most of them will agree with me. So if you're going to say that you have an imaginary number, what you really should say is you have some number which is the coefficient of an imaginary unit. And you multiply the imaginary unit with the coefficient. That's the correct way to say it. However, you know these modern people, they don't want to say it that way. Well, I'm sorry. It's just not right. I will cover this in the next lesson. I promise you, I will definitely cover this in the next lesson. So, I would like for you to stay tuned because there is more to come.